Hello everyone, this is the week 2 of Professional Cloud Architect Study Group. I am Mustafa Moradian. I'm a senior backend engineer at Grafana K6. I'm about to present the week 2 of the Professional Cloud Architect exam. And together we are going to learn a few things and also give you a little bit of homework for the next week and give you 1 week to prepare for the next. I'm available on Twitter, LinkedIn, and I also have a blog at mustafa.dev. That's my Twitter handle, by the way. But if you search my name, I'm all over the place. Yeah, these are the people from GDG Cloud Oslo and GDG Bergen, and also GDG Cloud Stockholm, who are going to present the next weeks. Last week, Mariana presented, so week 1. This is week 2, and I'm going to present this week. These are what we are going through today. So where we are, a little bit of exam guide review, a few sample questions, Q&A, and preview of actions for next week. Okay, where are we? We've done some initial work of preparing. So we had an intro session and we talked about what this is, what it entails, what you should do, what are our responsibilities, what are yours, what are we going to do, and the whole purpose of this study group. So this is the second week. I will give an overview of the last week and also present this stuff in this week. This is the week 2, and week 2 contains these topics like designing and planning a cloud solution architecture, which entails meeting business requirements, technical requirements, designing network, storage, compute resources, creating a migration plan, and at the end, envisioning a future solution improvements. I hope that you've gone through the last week's material and you've already know what GCP is, what a virtual network is, what a virtual machine is, but I'm still gonna give an introduction to many of these terms. First of all, is that you should know that when you're using cloud resources on GCP, you're dealing with something called a region, and in each region you have zones. A region is usually either a few countries or a continent, and it contains a lot of zones, and those zones are basically data centers providing these cloud services for you. The inter-region, or basically interzone connectivity and network, is very high speed, so it will give you less than 5 millisecond latency, and you can have all sorts of distributed workloads in those zones in a specific region. But when you're expanding beyond the region, it's called a multi-region. So you have to plan it ahead because it is costly because of the network costs and also other costs that might entail. Because when you have a resource in a single region, in a single zone, that's just one resource that you're paying for. When you want to make it redundant or want to scale your resources to be able to serve different customers from around the world, then you have to pay extra. So that's to keep in mind for planning and next steps. Again, in the foundation, we've learned that there are 3 VPC network types in the last week, if you've gone through the labs. There's the default mode and the auto mode. Usually these are used for training and test and staging when you want to just do something and you don't care about the internal network details of subnetting, of CIDR, of routing, of firewalls and stuff. If you don't care about them, when you create a project and create a resource, especially a compute engine resource or some other source of VM or container, they are assigned a default or an auto mode network. So the auto mode and default is different basically based on the subnet. So default is just one subnet per region, but in auto mode it's in /20 and it's expandable. So you can expand it up to /16. I will explain what these notations are in a little bit. But usually when you're planning your own infrastructure, you want to manage your own network. So that's where the custom mode comes in, where you create your own subnets, you have full control of your IP range. The IP allocation is done based on regions, so regional IP allocation, and it's expandable based on RFC 1980. You might be wondering what these are, and I will explain very shortly. If you haven't been into networking before, or if you don't have a background in networking and you're wondering what these terms mean, what is a subnet, what is a network, what is a firewall, what is I don't know what all of these terms mean, I highly recommend you to do 2 things. First is either go through the professional cloud network engineer exam guide. So there are a lot of things to learn here. Or if you want to start and learn network from scratch, if I don't know, for example, you don't know what WAN is, or you don't know what BGP is or what it means, I highly recommend this CompTIA Network Plus certification exam. You don't have to take the exam, you just have to go over the objectives. So if I like go a little bit down, there are like networking concepts, protocols, ports, and physical, all the layers of networking, all sorts of, routing, switching, topologies, IP addressing. And one thing I just wanted to highlight here that is very well explained, I think, here is the classful and classless notation for subnetting. So in an IP network, I'm just talking about Internet Protocol Network, which is the third layer in the OSI layering, terms. You want to have networks and you want to divide them so that you can have separate machines and containers and stuff in separate networks so that their traffic do not collide with each other. So what you do is subnetting. There's a historical way of doing this subnetting, which is called classful subnetting. It is, I would say, dead now, sort of, where you have these old classes, so class A, class B, C, D, E, and then these classes explain or refer to the network bit of the subnet. So IPv4, I'm specifically talking about IP version 4, which is 32 bits. This 32 bits has two separate components. So the first component, which is the leftmost bits, are called the network or network bits, and the rightmost components are called host bits. So these classes basically mean, like when you're talking about class A, it means that your subnet has 8 bits on the left as ones. So it's 255.0.0.0. If it's class B, it's 255.255.0.0, and so on and so forth. But as you get a little bit more advanced in networking, you might want to consider VLSM and CIDR notations, which are easier to explain, easier to mention. And usually most of the components and networks and stuff, usually they work based on CIDR notation. And you usually see CIDR notation in exams and all over the place, all over the internet. And CIDR is called classless interdomain routing, and it refers to the way that you show IP addresses. So if I go here, ES/20 means that you have a network that has 20 bits on the left-hand side of your IP address assigned to the network bits. And the rest, which are like 12 bits, are hosts. So 2 to the power of 12, then you can count the number of IPs that you can use. Like if I, like, for example, go with this IP address and I calculate, I get, this is the CIDR range that I entered. I get the net mask of 255.240.0. The first IP is 10.0.0.1. This is the network address. You cannot use it to assign it to a node. This is the last address in this range. So the next range starts with 10.0.16.0, which is the network. 10.0.16.1 is the first IP on the next network. So the next network cannot be able to see this network unless you have a router in between, or you have some other, I don't know, NAT or something. And the total hosts in this network is 4,096. In Google's terms, however, not all of these are usable. So you should deduct 4 IPs from here, because the first IP is the network. The last address is the broadcast. You cannot assign it basically to any node. This is used by all nodes on your network when you're broadcasting. And also the first IP address is, when you are creating a VPC, is called a gateway address usually, because these are mapped in the internal VPC, structure. And you can use that to have, like, connect your nodes to the internet if they have access or anything. And also the second to last address, so 10.0.15.254 is called the second to last address. That's also a reserved address by Google in your VPC that you create. So be aware of these notations and learn more about them, because you will see them like literally all over the place in your exams everywhere. So VPCs or networks isolate systems. What this means is that if you have 5 networks or 4 networks and your nodes reside on the same network in the same project, so the project is the combination of all the resources you use in your cloud account. So you create a project and then everything goes from there. In your project, you can have multiple networks. And in those networks, no matter where your nodes are located, in which region, in which zone, if they are in the same network, it is said that they can see each other. This means that they can ping each other, they can send traffic to each other, and they can basically see each other in the network. But if you have nodes in different networks, like nodes C and D that you can see, they have to use a public IP address and the internet to route traffic between each other. So this is very important because this costs you egress, money or egress costs for you if your traffic goes through the internet instead of inside the network of Google. So keep that in mind when designing your network. Yeah, so the next thing you should know is that VMs or compute resources have internal and external IP addresses. So an internal IP is allocated by DHCP, Dynamic Host Control Protocol, which is a service you probably have heard it already, that assigns IP addresses to nodes on your net in that same IP range. These are assigned or renewed by they expire in 24 hours. So you will get a new IP address in the next 24 hours. And your VM name and IP address will be registered in the network scoped DNS. So the DNS that just works inside your internal network. Then there is the external IP address or public IP address. There are 2 types of these IP addresses. You either have them static or reserved for you. They do not change. You have them reserved for you and you can use them to access your nodes from the internet. Otherwise, you can have them not reserved. Depends on the use case, but usually sometimes it's a good idea because like if you have an on-premise network which is behind the firewall and then you want to open a port on your firewall to have access between your cloud infrastructure and on-premise, then you need to have an statically reserved IP address that is accessible from your firewall DMZs. But otherwise you can have a public IP address assigned to you based on a pool which can change. One thing to keep in mind is that your VM would not know the external IP address because it's mapped to the internal IP address. This is usually not the case when going bare metal. So in a bare metal infrastructure, you set the IP address to the server you have, and then you have control over your IP address. So we talked about networks and subnetworks. In order for these networks to talk with each other, you have to have routing in between. So routes, which are basically addresses that specify network, if you look at like this. So 192.168.50/24 refers to the network that has the first IP as 5.1 up until 5.255. So if you have this route in your VM routing table, then when the traffic wants to go out, so it's an egress, it's not ingress. So it goes from your VM to the outside. Then it will look up the routing table and it will select the most specific route to forward the traffic to. These routes are created when you create a subnet. So most of these are already assigned to your VM when you create a VM, which basically why and how your network and your VMs can see each other in the network. So the destinations are in CIDR notation, so /24/20. And this is the default gateway to access the internet, 00/0. Also, keep in mind that there might be firewall rules preventing you from accessing the internet or vice versa for internet users to be able to access your node. So firewall is also very important for traffic delivery. Okay, so I'm going to go to the case studies. These are the 3 important case studies you should learn for the exam. The purpose of this case study is for you to understand the business requirements and translate them to technical requirements. And that's the whole purpose of, I would say, this exam and this whole thing. And being an architect means that you understand business requirements and can convert them to technical requirements. So the first one is a gaming company called Mountkerk Games. They have a few key business points. So they are an online gaming platform which became popular very quickly. They need to scale up. They have a lot of app servers, MySQL analytics and stuff. They already have a plan in place for the general design of the infrastructure and some requirements, but they had issues with the previous cloud provider. Their immediate business goals or business needs is to increase the global footprint because their business is growing, so they should meet the demands. They should improve the downtime because of the same exact reason. And they need speed, stability, and deeper insight. So technically, they have this existing environment in data centers. They have a lot of on-premise servers and stuff. They do not want to replace them immediately. That's very important. So pay attention to each single word that is mentioned. And they want to deploy this cloud service only for the new games that they develop. So the technical watch point is that they should probably use compute engine for this with hardened Linux distribution. They need auto scaling and low latency. They need load balancing, and they need it globally because of users being all over the place on the planet. They also need to have backlogs of everything so that the data is not lost. They're using MySQL database that needs to be replaced, and the reason is that it cannot grow more than a few terabytes, like 10 terabytes or something. So they're having scaling issues, and they're thinking about moving to a managed service that is like hopefully no SQL. They want transactional DB for profiles and states, and they want to have querying of like 10 terabytes of historic data for all sorts of leaderboards and stuff. And they also need time series database for analytics. Currently, the statistics are written to file, done some ETL on it, and then stored in MySQL. And they also create reports from them. For data ingestion, they need live metrics from the game server. They might have late data due to slow mobile networks, and they need to regularly upload data from those mobile devices. The next one is dress for win. I'll not go too deep into this like the last one, so I'll keep this as an exercise for you to just read all of these and go through them yourself. Their business is as an online web-based wardrobe management service. They have a web UI mobile application, a social network of some sorts. They monetize with ads and e-commerce referrals and stuff. They've grown from 10 servers to over 100 servers. They're seeing some issues because the capacity for handling this future growth is not enough. They are deciding to move to the cloud, and they also want to have a disaster recovery site so that they do not lose their data. The immediate business goal is that they prefer managed services because it lowers the overhead and lowers the headcount needed to manage those services. And the considerations is that is the competition, how new features are added, that things are elastic in scale very quickly, and the cost. So these are the things they have in mind. Their existing environment contains of two databases, MySQL and Redis. They use MySQL for static data, clothes and stuff data, user data, inventory and stuff. And they use Redis for social graph metadata and caching. For this, they can store their static data in a relational database, and they can have an in-memory, like high-throughput solution for social or metadata caching. I will explain this later a little bit. They have Tomcat, Nginx, and Apache Beam for their application servers. They probably want to move to a microservices-based architecture. They also want to serve static content. And since they're already using VMs, as is mentioned here, they kind of can do lift and shift. So lift and shift means that you back up your VMs, you migrate them with VM Migrator to the Google Cloud, and then you set up some basic things like networking and stuff, and then your servers are on the cloud. That's it. It looks easy, but it needs some work. But that's how it's done: lift and then shift. So as I mentioned, they're already using virtual machines. So they're using iSCSI for SANs. Their SANs. They're using Fiber Channel for their databases because they need high throughput, as already mentioned. They have 1 petabyte of storage, of which 400 terabytes are available. They use NAS for logs and backups and image storage. They have 100 terabytes storage, of which 35 gigabytes is available, which is not too much, so they need to move quickly. As I mentioned, they already use VMs, so lift and shift should be done so that they can quickly scale. and they need to use different classes of storage that I will explain later. They also use like Hadoop and Spark and a few message queuing services. They have a requirement for networking, encryption, security scanners, CI/CD, and there are Google services that provide those features, which I'll explain. The next one is a company in mining and agriculture that has a lot of dealers all over the planet. They're going to grow globally. So the pattern you might have seen already is that all of these companies want to scale and grow. And this is why an architect comes in and analyze and investigate, business requirements and try to propose plans for growth, at least in the IT domain. They want to decrease their downtime from 4 weeks to an average of less than 1 week. Also, they want to give their dealers, which are like 500 dealers, more visibility into the data of customers. And they want the ability to partner with different partners in the agriculture industry. They're already using Linux-based OSs in data centers. They're using gzip CSV files. They upload them to FTP servers, do some ETL on it, and do data warehousing. So they store all this data somewhere. There's 3 weeks of delay to serve those data back, and all their vehicles that they have are connected to a cellular network. So they have a lot of vehicles, 200,000 something. They want to be able to handle 900 terabytes per day of data. They do not need low latency in their I/O, and they have 120 fields of structured data and a lot of smart machines. Their vehicles upload 9 terabytes per day over cellular networks. They might have potential outages, so this should be taken into account. And there are a few other things to take into account, like data visualization, batching, and dumping data into somewhere to store. That was that. Now is the week 2. So let's go to this week. So this week I talk about the core infrastructure, or basically the services that Google provides. These are only a handful of those. It's 120 something, I don't know, 200 services. So I'm just going to mention a few of those that are important for us. First of all is the compute resources that you can see here. I'm going to go over them, and then storage, big data, and hopefully machine learning. I'm not sure about that. Okay, so Google Cloud has a lot of offerings in terms of compute or processing, basically, as it's called, compute. Each serve a different purpose, each fit in a different scenario. You can fit all of them into all your own scenarios, but you should also take into account the management overhead and all the things involved. So be mindful of that the management overhead and also the cost, and a lot of these are involved. So usually people move to cloud to decrease the management overhead or remove the management overhead of their services and infrastructure, not to increase that, unless you have a good explanation for why you move to a service that needs more management. Okay, so in the infrastructure as a service, or IaaS service, Google provides compute engine, which are basically VMs. You can migrate your VMs, vSphere VMs, VMware vSphere VMs, EC2 VMs, and I think one other type can be almost easily migrated to compute engine. You can then migrate your workflow into cloud pretty much quickly. The second is the hybrid solution of Kubernetes. Kubernetes is an orchestration and a management engine for containers and huge workloads that span over multiple regions, multi-regions and stuff, and can give you the ability to have ephemeral workloads on all sorts of different things, and can manage your containers, take care of them when they die, spawn a new one, scale very quickly, so on and so forth. It has a lot of features. I cannot mention all of the features in just one slide. I just want to mention that there's the GKE or Google Kubernetes engine that you can use to have a managed service for Kubernetes. Then there's App Engine. So App Engine is also another offering. It's a platform as a service that you can run your code on it, run your web service or something that you've written in Python or PHP or Go or Java, and then let App Engine handle everything. So The good thing about App Engine is that you don't need to manage anything. You just upload your code and it just works out of the box. That's the purpose of App Engine, so that you don't need to think about scalability or reliability or anything. You just think about your code, you just think about what you want to develop. The rest is handled by Google. The next thing is Cloud Run. So Cloud Run is a way to manage containers. So if you work with services such as Swarm, like Docker Swarm, which I think is not used anymore, not sure. So this is a container management solution where you can let Google take care of your containers and manage them. The last thing is the Cloud Functions, which is serverless. So you upload your functions and you wire them up and they just work. That's it. So how do you decide? How do you decide which of them is fit for a purpose? I would say if you are learning for professional cloud architect exam, you already know that. But in case you don't, which is fine, perfectly fine, you usually decide based on what you want to do and which goal you want to achieve. Do you want to have access to everything, to the kernel, to routing, to networking, to all the details of everything? You want to manage everything yourself. You want to have long-lived VMs. So you want to have physical servers or long-lived VM on physical servers. That's the compute engine. If you want to manage VMs, that's your choice. Of course, you can run containers on the VM, but the more containers you run on a VM, the harder it gets to manage them. So you should manage them either manually or have some sort of something that can manage these things. If you want, as it said, rich administration of container workloads, you should go with Kubernetes. Kubernetes takes time to learn, so it's a steep learning curve. And when you get to know it, it kind of looks like other services that can manage containers. And it's not a fit for everything. So just keep that in mind, that whenever or wherever you see something, you just don't say, we have to use Kubernetes. Kubernetes needs a lot of work to do it right. It needs monitoring, all sorts of tracing, all sorts of management stuff. All of these are managed already by the Kubernetes engine by Google. So half of those maintenance and management stuff is handled by Google. The rest you should take care of. The next thing, which is a no-ops solution, is the App Engine. So as I said, you can either run your containers or your code on the App Engine, and it just works. The next thing, which is a managed service, and you can run your stateless containers on, is the Cloud Run, which Google is, I think, pushing for it a little bit. And they want to use it for a lot of workloads, especially those people who do not need a complete Kubernetes implementation, that sort of orchestration, they can go with Cloud Run. And the next no-ops thing or no operations thing is Cloud Function. Like, for example, you want to have a service that runs when a user uploads a file, and then take that file, convert it to some format, and then upload it on an object storage. That's what Cloud Functions are for. I mean, they can do also complex work, but their purpose is to serve a certain goal and do it right. That's it. Let's start with a question. You're considering deploying a solution using containers on Google Cloud? What Google Cloud solutions are available to you that will provide a managed compute platform with native support for containers? Okay, let's see our options. I would go from the last option. So compute engine auto-scaling groups. So compute engine are VMs, and auto-scaling groups are groups of VMs if you want to scale your workload. It doesn't natively support containers. I mean, you can run containers on your VMs, but then you get to manage them yourself. That's the gist of it. It's not native support for containers. It's not a managed platform, as you also see here. So managed compute platform with native support for containers. So this is incorrect. The C is container registry. So container registry is a place where you store your containers, so then you can fetch them into Kubernetes or Cloud Run or any other place you want to use them. So this is not a compute platform. It's a storage for your containers. So that's incorrect. Then there's Cloud Functions. So Cloud Functions, I suppose they do not support containers. So that's also a no-go for us. Google Kubernetes Engine clusters are clusters of GKE, which has native supports for containers. I mean, the whole thing is based on containers, and it's a managed compute platform. So that's that. The next thing we're going to go over is the storage. Okay, so there are a few different storage solutions on the cloud. I just mentioned a few. There's the cloud storage, Cloud SQL, Cloud Spanner, Cloud Data Store, and Cloud Bigtable. Then how do you decide which storage to use for your data? So when we get to know the type of these services, because their name might not say much about them, but their type might give you an idea. The Cloud Data Store is a NoSQL document-based database. Imagine MongoDB or similar. It has transactions. It doesn't support complex queries as does like SQL, where you can, join multiple tables, multiple views and stuff, and then get the results. That's not something that is supported by document-based databases. It can hold terabytes of data, and each entity is 1 megabyte, I think maximum, or can be. So the next one is the Bigtable. So it's a columnar NoSQL database. Imagine Cassandra. It has single row transaction support. It doesn't support complex queries because it's columnar, and it has petabytes capacity. Each cell can be like 10 megabytes, and each row roughly 100 megabytes. So these are used as database solution for your data. The next is the cloud storage, which is a blob store. You use it to store binary data, files, or whatever you want to store, like logs, backups, and stuff. It doesn't support transaction. It doesn't support queries. It can hold petabytes of data, and the largest object size is 5 terabytes. So if you have a file that is over 5 terabytes, then you should split it into 5 terabyte chunks. The next thing is Cloud SQL. It's a relational database. I think it's MySQL database. I'm not sure. Correct me if I'm wrong. It supports transaction. It's SQL-based database. It supports complex queries and stuff, and it has up to 10 terabyte storage size. It is increased to 15 terabytes now, but I suppose in the exam you will see it as 10 terabytes. And the size is determined by the DB engine that you use. Yes, Simon also mentioned that it's also Postgres that you can use. Yeah, and MS SQL. Okay, so it's basically a wrapper around all those databases. Fair enough. Then there's Cloud Spanner, which is the Google solution for a horizontally scalable database. One thing to mention is that these are SQL databases and relational, and they're used for online transaction processing. So basically, they're used for cases where you need to have data stored very quickly and retrieved very quickly. That's their purpose. It also supports transaction and complex queries. It can hold petabytes of data, unlike Cloud SQL, which can handle terabytes. And each row size can span gigabytes. The next thing is the BigQuery, which is a relational SQL database for OLAP. OLAP is online analytical processing, which means you want to store the data and eventually query them. Not that you want them to be like online and store data each second, like thousands of rows of data per second, and retrieve them at the same time. So you want to use them for analytics and those kind of workloads. It doesn't support transactions. It can support complex queries, and the capacity is petabytes, and the unit size is 10 megabytes per row. Okay, so how do you select your storage? First, you should see if your data is structured. If it's not, then it's probably a blob. You either store it on a cloud storage for Firebase or the cloud storage, the normal cloud storage, if you are not using a mobile SDK or something. If it's structured, if you want to use the analytics workload, if you want low latency and quick updates, you go with Bigtable. Otherwise, you go with BigQuery. If you don't want to use your database, your data is not for analytics workloads, there are two options. Your data is either relational or not. So if it's relational, you either want to scale them, you use Cloud Spanner, or you don't, so you use Cloud SQL. And if your data is not relational, depending if you're using to develop mobile apps, you either use Firebase real-time database or Cloud Data Store. This is how you decide which data store to use. So There are two ways to deploy your applications on Google Cloud. One is the App Engine, which has two environments: the standard environment where there are a set of runtime supported like PHP, Python, Go, Java, something. And then you get instance startup. You don't get SSH access. You cannot write to local disk or anything. It doesn't support third-party libraries and stuff. It does support network access, and the pricing model, after you use your free daily use, you pay per instance class with automatic shutdown. If you want to run your own runtime, or you want to use third-party libraries, or you want to have SSH access to your instance, then you go with the flexible environment, which takes minutes to start up, and it's different. So it depends on your use case. There's also the Kubernetes engine. So Kubernetes is different. So App Engine is a platform as a service, which is usually used for web and mobile applications and container-based workloads. But Kubernetes is only container-based. And, there are differences. You cannot compare them. It's like comparing apples versus oranges. It's not a good comparison, I would say. But just keep that in mind. If you want to have a managed infrastructure, you go with Kubernetes. If you want to have a dynamic infrastructure managed by Google, then you go with, or you want to manage them yourself, you go with App Engine. Of course, with all cloud solutions, there is tools to deploy, develop, monitor the cloud services you have. And on Google Cloud, it's called Google Cloud Operations Suite. It used to be called Stackdriver. So if you've heard Stackdriver in the exam, this means that it's Google Cloud Operations Suite or Ops Suite. And it contains a lot of, logging, tracing, monitoring, error reporting, debugging, profiling solutions, and you can use them for your own good. And I think there's this professional cloud developer exam. So if you want to go deep into these things, you should probably go over for that exam. So this is just so that you know that there's something for monitoring, something for logging and stuff. The next thing is big data and machine learning. There's a few different services offered by Google Cloud. There's Dataproc, Dataflow, BigQuery, PopSup, and Data Lab. They serve different purposes, but basically they're managed services for either batch processing, micro batching, or stream processing, depending on your workload. And each of them serve a different purpose. I'm not much into machine learning and big data, but if you're interested in machine learning, there's Zahra and a few other people from our group and a few from other GDG groups. They're preparing to have a study group for machine learning and AI. So feel free to jump into that and register so that you can get to know more about these services. Okay, sample questions. Let's review a few questions. Your organization has a 3-tier web application deployed in the same cloud, virtual private cloud, Google Cloud VPC. Each tier, so a 3-tier means web, API, and database are separate from each other. So each tier scales independently of the others. Network traffic should flow through the web to the API tier and then onto the database tier. This means that traffic should not flow between the web and the database tier. So people from the web application should not directly access the database. That's the gist of it. How should you configure the network with minimal steps? Keep that in mind that it specifically mentions the minimal steps. Option A, add each tier to a different subnetwork. So this is a little bit tricky because you can do that, but then you have to configure networking, configure firewall, and do all these steps to manage this thing, which is not minimal steps per se. So that's the incorrect answer. The second is set up software-based firewalls on individual VMs. So that's basically saying the same thing, but from a different perspective. So you can have firewalls, but then they're on individual VMs, and then you have to have routing set up, you have to have everything set up for you to work. So it's also not minimal steps. Doesn't necessarily mean that it's incorrect. It means that this is not our answer. This is partially correct. The next is add tags to each tier and set up routes to allow the desired traffic flow. So what are tags? Tags are when you're configuring your VPCs you create firewall rules, and then you assign tags to them. And when those tags are assigned to your VMs, or your workloads, your compute services that have access to network, then you can let them access each other based on if they have that tag or not. It reminds me of the old days of VLANs, but you should set up routes yourself. The next is add tags to each tier and set up firewall rules to allow the desired traffic flow. This is the correct answer, because when you do this and you assign tags to your containers or to your VMs, then those get to talk to each other. So they're on the same network probably, and then they will see each other, but they won't have access to each other because of the firewall rules. But then you have tags assigned to them, so this causes them to be able to access each other. So web will only see the API, and API will only see the database. So web won't be able to access the database. These are the labs for the next week. And that's it. That's a wrap. Thanks for listening. Thank you.